Okay, so somebody finally asked me some questions, so I'm going to address a few things from the final review sheet. First of all, I was asked just for the answer for number two. So number two is the Cauchy-Schwarz problem. The maximum possible value is 50 over 7, and this occurs when A, B, and C take these particular values. Um, so, yeah, let me know if you can't get that one. On number three, I'm just giving the answers as in true or false. Of course, there's more to the problem. You have to, like, explain it and stuff, but I was asked just for, like, an answer key. So, yeah, it just goes true, false, true, false, true. Also, number nine is actually in the book. You can see theorem 7.16 on page 142. Which proves that equivalence modulo n is a congruence modulo n is an equivalence relation. So yeah, I can say more about those if you like, but I wasn't really asked too much about those, just for like where are the answers. So then I'm going to give more of an explanation for a few more problems, like number 5C. So number 5, you're asked to find all values of n such that this inequality holds. And if you've tried this one at all, you probably tried, and this is how we always start, you start trying to plug in a few values of n just to make a guess. And you will find that n equals 1 does not work because 4 is not greater than or equal to 5, but n equals 2 does work. And typically, our guess is, unless we know any better, our guess is that once we find a value of n that works, then probably all the values of n after that are going to work. Sometimes that's not true, but this is we try to make the easiest guess possible. So let's make that guess and see if we can prove it. So this would be a proof by induction. The base case is the first value of n that we're making a claim about, which in this case would be 2. And of course we already know, like, we already checked that this works for n equals 2, but indeed it works. 16 is greater than or equal to 4 plus 9. For the induction step, we assume 4 to the n is greater than or equal to 2 to the n plus 3 to the n. And if it helps, we can assume that n is at least 2. I mean, sometimes that helps because we're only proving it for n greater than or equal to 2. This may or may not help. We may or may not use that piece of information, but it doesn't hurt to write it down because it's true. Then, well, what do I want? I would like 4 to the n plus 1 to be greater than or equal to 2 to the n plus 1, and then 3 to the n plus 1. So maybe now I'll do one of these typical deals where I leave myself some space, and in the end I write greater than or equal to 2 to the n plus 1 plus 3 to the n plus 1. And because I'm so optimistic and ambitious, I'm going to go ahead and put a proof box, because as long as I fill in the missing logic, this will be the end of the proof. So I have to get from there to there. And we've done this a few times. We know that maybe this is a good idea, because I would like to relate 4 to the n plus 1 to 4 to the n, because I have information about 4 to the n. So I write this, so then this would be greater than or equal to 4 times, and then I'm going to replace 4 to the n with 2 to the n plus 3 to the n. And now, to get from here to here, of course, 2 to the n plus 1, that's just 2 times 2 to the n. And this is just 3 times 3 to the n. So actually, I think I can see it from here to here. Because if I multiplied this one by 2, I would get this one. But I'm not multiplying it by 2, I'm multiplying it by 4, so it would be even bigger. And if I were to multiply this one by 3, I would get this one. Of course, I'm not multiplying this by 3, I'm multiplying it by 4, which makes it even bigger. So I think I really see it from here. So what should I write? Maybe I can distribute the 4. So I distributed the 4, and now I can say this one is, so 4 is greater than or equal to 2. So I can write 2 times 2 to the n here, and I can write 3 times 3 to the n here. And then that, well, this is actually equal to this, but it's not wrong to write greater than or equal to, so maybe I'll just leave this. This could be an equal sign, because of course this is exactly equal to this, but greater than or equal to is also true. So yeah, so that's it for this one. Let's see, this video is only 6.5 minutes, so I can keep going. So I was also asked about number 7, which is some prove or disprove statements about GCDs. So the first one is this, which I believe this was on part of your homework, I think. But in any case, this one is true. And here's how you prove a statement like this, the statement that a GCD of these two numbers equals the GCD of those two numbers. We'll prove that if you have a common divisor of A and B, in other words, I have a number D that divides A and it divides B, then that's the same, or it's logically equivalent to saying that we have a common divisor of these two numbers. And that would do it. Like, we just show that any common divisor of these two numbers must be a common divisor of these two numbers, and vice versa. Any common divisor of these two numbers must be a common divisor of those two numbers. And that's enough to prove this. So we have to actually prove this, though. So this is a if and only if. This is like a bidirectional logical statement. So I'm going to show each implication separately. So I'm going to show that this implies this, and then separately I'll show that this one implies this one. Right, so assume D divides A and D divides B. Then I would like to show that both of these statements are true. Of course, I already know that this one is true. That's one of my assumptions. So that's I get right away. This one is, yeah, this is easy enough. If D is, like if each one of these numbers is a multiple of D, then I add them together and it's still a multiple of D. That's a basic fact that we learned. If D divides A and D, whoops, I don't really need that parentheses, but if D divides A and D divides B, then D divides A plus B. To show the other way, I assume these two things and try to prove these two things. Of course, one of the two things that I'm trying to prove is already one of the things that I was assuming. And in fact, over here I'm assuming that, in particular, D divides B, so, of course, D divides B. To argue that D divides A, let's see. I know D divides A plus B, and I also know that it divides B, right? Because I know that D divides A plus B and B. So if I know D divides these two numbers, that when I subtract these two numbers, D should divide that. That's another property of divisibility. But of course, the reason why I'm subtracting these two numbers is because the B cancels, and I get that D divides A, which is the other thing that I was trying to prove. So that's it. We showed that D is a common divisor of these two numbers if and only if D is a common divisor of these two numbers. What about 7b? This is still prove or disprove. But now it's this, which, yeah, so I would encourage you, for a prove or disprove, I would encourage you to, like, unless you already know the answer, to just try plugging in a few numbers to see whether it's true. With this one, you're not going to be trying very long before you realize that this is false. Like if A is 1 and B is 1. The greatest common divisor of 1 and 1 is 1. If I were to do this, I would get the GCD of 2 and 0. And the GCD of anything with 0 is itself. Right? So already I have a counterexample. This doesn't equal this. So yeah, maybe I won't say too much more about that one. Let's see. Yeah, I can probably do part C in this video. So for 7C, it was that GCD of 2A and 2B equals 2 times the GCD of A and B. So in the interest of time, I encourage you to try plugging in a few numbers for A and B and see what you get on both sides. If you try that, you're going to find every single time that it's true. So in the interest of time, I won't go through that, but I'm just pointing out the fact that you can try a few numbers and figure out a good guess that this is a true statement and then try to prove it. So let's skip that part and just try to prove it. So we'll prove that if D is a common divisor of 2A and 2B, that this is logically equivalent to saying that wait, how should I say this one? Yeah, so maybe, so for this I want to show that maybe if D is a common divisor of A and B, yeah, so maybe here's how we'll say it. So D is going to be a common divisor of A and B, and then I'll show that that's logically equivalent to saying that 2D is a common divisor of 2A and 2B. Yeah. Okay. So for the forward implication, let's assume this. Yeah, then, well, so this feels like this proof is going to be pretty easy. Yeah, so yeah, so let me, I'll still show some work. So, right, I just need to show that 2D divides 2A, which is pretty obvious, but I'll show some work. So there exists two numbers such that like A is M times D and B is N times D. So then, you know, 2A would just be 2M times, whoops, M times 2D. That's how I want to write it. And 2B is N times 2D. In other words, this is a multiple of 2D, and this is a multiple of 2D. So we get this. For the other one, it's just as easy. I'm going to assume these two things. So 2D divides A, oops, 2A, and 2D divides 2B. So there exists some M and N where, let's see, this is M times this. And this is N times this. And then I just want to show that D divides A and D divides B. But that's easy. I can basically just cancel the 2's. So A is M times D. B is N times D. So D is dividing A and D is dividing B. Yeah, so that one's true, and we proved it. Okay, so this video is now approaching 20-ish minutes, so maybe I will cut it and make another one.